Okay, welcome back. Happy Wednesday. Today is the 1st. We are covering graphical and numerical antiderivatives today. I want to point out that our very first project is going to be collected next class. That is this coming Friday. You will hand me the first project. As usual, you are encouraged to work with each other on the math projects and with folks in Math Studio and with me, anybody you want to. But a real good idea to check answers with your neighbors before you turn this thing in on Friday. Also on Friday, I'm going to hand you our very first quiz. It is a take-home quiz, and you will hand it back to me on Monday. So quiz number 1 is going to be due on Monday. We'll talk about the quiz on Friday when I give it to you, okay? Any questions on the calendar? Okay, so before we jump in, and again, we're on page 31 here, there are a couple of logistical things we need to talk about. So you're going to grab, I think it's 3 things in front of you. So first, make sure you grab one of the Math Studio bookmarks, nice and bright. So as you might know, this is the schedule of when the Math Studio is going to be covered by math faculty members. So you're welcome to go in and ask them for help on any of your questions on homework or on projects or just sort of studying in general. If you're more of a digital person, take a photo of this thing and then you don't have to carry around a bookmark. Right, so there's that. Another handout is this guy right here. It says homework as assessment. It's 1 page. This is something I talked about at the end of last semester. I think a couple of folks really read it and maybe gave it a shot, but if you didn't, I'm pushing it again. I think it's a really good idea to try reframing the way you think about doing homework according to the techniques in this document. So if you didn't read it last semester or you read it but kind of forgot about it, I encourage you to give it another shot. Okay, and then the last handout is this little scrap of paper here. And so I want to say that on your syllabus, I printed out the syllabus and then I made some changes to the grading scheme. And then I forgot that I needed to reprint that page. So the percentages that I gave you on your syllabus are not the percentages we are doing. We are doing these percentages right here. So if you find the thing with the percentages in your syllabus, you're gonna just tape this guy right over the top. 2 homework options. I talked about these the other day. I only realized after the fact that you still had the original percentages. All right, so 2 options for your grading. We'll talk about these later on in the semester, but replace whatever is in your syllabus with this. These are the 2 choices, right? Okay, and then one more thing about the syllabus before we jump into the math. I had said the other day that I will take your homework up to 1 week after it is due. That is not my policy. My policy is written correctly in the syllabus that you have, and it says very clearly, I will accept homework up to 1 class after it is due. That is the policy, and that's what we're going to do this semester. We'll give you a little bit of leniency if you're not ready for today's homework because I misspoke. I said 1 week after. 1 day after is what I intended. When I said 1 week after, I was quoting the late projects policy. I accept late projects up to 1 week after. So the homework, like I said last semester, I let folks do it all the way up until the test that the homework was on, and I think that led some students to some bad habits of waiting until the last minute to do all of their homework. So this is my way of trying to strongly encourage you to do the homework on a regular basis, but giving you this 1 class leeway because I know sometimes life gets in the way. All right, any questions on that? Okay. So let's jump in again on page 31 with our summary. In this class, we introduce antiderivatives and we revisit from last class how to create values of a function using the Fundamental Theorem of Calculus Part 1. We also draw graphs of functions based on the graphs of their derivative. Number 1, let's find an antiderivative of 2x plus 3. Antiderivative of 2x plus 3. So what we are looking for is some function where when you take the derivative of that function, you get 2x plus 3. Let's take them in turn. 2x, what function did it come from? X squared, right? Because the derivative of x squared is 2x. And then I'm going to put a plus because derivatives act very nicely on additions and subtractions too. Where did 3 come from? 3x. And so that right there is an antiderivative of 2x plus 3, because if you take a derivative of that thing in blue, you get 2x plus 3. Are there any other antiderivatives of 2x plus 3? Yeah, so let's be really specific here. Plus 5. Great. Because when you take the derivative of that plus 5, it becomes 0. And plus any number is really the most generic thing. So actually, if you give me a function, it's going to have infinitely many antiderivatives, right? Because there's no way of knowing if there was a number floating out here at the end. And so the general antiderivative of 2x plus 3 is the family of functions x squared plus 3x plus c, where c is an arbitrary constant. You can pick any letter you want. Most often we're going to pick C. Finding antiderivatives is at the heart of a lot of what we're going to do this semester. They're going to get a lot harder than 2x plus 3. But the idea is going to be the same throughout. I'm going to give you a function, and you're going to say, oh, Ian took the derivative of this other thing, and that's how we got the function he gave us. Okay, number 3. We're going to talk about some graphing stuff. Let's review the relationships between a function and its first and second derivatives, again, focusing on graphing. So f prime is greater than 0. This double arrow means if and only if, means these two statements are equivalent. So f prime is positive, means f is increasing, right? You got a function with upwardly sloped tangent lines, then the function must have been increasing, and then conversely, if you have a function that's increasing, then the tangent lines must be positively sloped, right? And then on the other side of that, f prime is negative, means the same thing as f decreasing, okay? All right, now we jump down to the second derivative. F concave up means the second derivative is positive, and f concave down means the second derivative is negative. That's old from last semester. It's actually this second side that's quite a bit more challenging for some folks. So I'm going to write some stuff over here. Suppose that I replace this sentence right here, but instead of calling it f, like a specific name, I'm just going to put like a generic box right there. So where it says f is increasing, I'm just going to say whatever's in the box is increasing, and then continuing to copy that first sentence there means the same thing as, and then box prime greater than 0. Agree? Just replacing the f's with boxes. Is that fair? So I can put any function I want in the box as long as I put the same function in both boxes. I have copied that sentence correctly. So the function I'm going to put in the box is f prime. Can you guys read that green? I just changed the green. I'm trying to get the good green. Is this readable in the back? It's not great. All right, we're still working on the green. Okay, I'm going to put f prime in the box. What do I need to put in the other box? F prime, right? As long as the things in the boxes are the same, I've got a true statement. So what this statement now says is that f prime is increasing, means exactly the same as what? F double prime is positive. And that's what it says here in the purple box. F prime increasing, F double prime is positive. There's a leap there. That stuff in the box is not as intuitive to me as the rest of the stuff we talked about. Increasing, decreasing for F, I'm all over it. Concavity for F, I got that too. But the relationship between F prime and F double prime, I really have to think about that. I have to pause. Okay, so if we want to work backwards from F prime to F, we're just going to apply what we already know in a different way. Let's give it a shot. Number 4, how do we sketch a function given a graph of its derivative? So for example, the graph of y equals f prime of x is shown below. Let's sketch the graph of y equals f of x. And the stuff that we're about to do here hopefully will kind of solidify part of project number 1. If you've already done a bunch of project 1, maybe just verify that the graphs that you drew satisfy the stuff that was written up above. And if you haven't started project 1, this should help you in terms of graphing, because the graph that was given to you in project 1 was a derivative, right? It was like a flow rate. That is a rate of change. And so I ask you to graph the antiderivative. It's the same idea as what we're doing here. Okay, so just a couple of things that are pointed out here on this graph. This graph right here is increasing for a while, then decreasing for a while. It's increasing again at the end, and there's a point of inflection right there near the middle. Okay, and one more time, this is f prime, and we're trying to graph f. So what we're going to do is focus on anything up here that has f primes in it, because after all, that's what we're given. So I see some f prime stuff right here. So let's start there. If f prime is positive, then the original function f is increasing. And if f prime is negative, original function f is decreasing. So let's first focus on that. This is f prime. F prime is positive or negative here in the beginning? Positive, right? It's both. How about in this next block over here? Positive or negative? It's still positive. Don't get distracted by the change in behavior. It went from increasing to decreasing, but that's not what we're looking at right now. You really kind of have to put the blinders on and focus on just one attribute of this thing at a time. So this graph is positive, all in here. And then this graph is negative, all here. And so if f prime is positive, what can you say about the graph of f? It is increasing. So we're just going to draw something that's increasing until there and then decreasing the rest of the way. So if you have pencil, you can draw in pencil. I'm going to make my first attempt and then I'm going to erase it at some point when I have a little bit more precise information. But I'm going to draw something very blocky here, increasing until, say, this guy right here. So increasing, and I'll just sort of arbitrarily put it somewhere. So increasing until I get to that point and then decreasing the rest of the way. And if you decided to take that graph and lift it up 5 feet or put it down 5 feet, all good. We have no way of knowing exactly where this thing is. All we know is it's increasing until that middle and then decreasing the rest of the way. Okay, now let's see if we can draw something that's a little bit prettier than that. That's the graph of f prime, and down here, yeah, I should label this guy. This is the graph of f. So f prime was positive in the red, so f was increasing in the same red. Okay, so the other information we had, again focusing on stuff about f prime increasing and trying to relate that to f. If f prime is increasing, then f is concave up. I'm sort of skipping over the f double prime piece, just trying to connect f prime to f. So any place f prime is increasing, f is concave up. So what that means, let's get rid of this stuff here. So f prime is increasing here to here, which means f is going to be what? Concave up. So I'm just going to kind of put like an arbitrary spot. So we're going to be concave up there, which my line is not. And then f is doing what here? It is decreasing. Should I have stopped it at the x-axis here? No, it is still decreasing. So we just shoot right on through. Again, you got to put the blinders on and focus on what you're after. In this case, it's just the increasing, decreasing nature of f prime. So in that entire space, which I guess goes to around here, what can you say? Because f prime is decreasing, f is concave down. So all of that space in there, we're supposed to be concave down. And then finally here, f is what? Sorry, f prime is what? Increasing, which means that f is concave up. Okay. Yeah, from the red to the blue, that entire space in there, we're going to make concave down. So all we have to do is just tweak it a little bit, get the concavity to match, but it still needs to obey the increasing, decreasing nature of the thing that we drew, right? And so this will be my second attempt at it. It'll be the last attempt at it, and then I think we'll be good. The linear thing was a very rough approximation. It was just a first attempt, but it's not linear. No, it's definitely not linear. For me, I need to break this drawing into two pieces. I need to think about the increasing, decreasing, which I've done with this very rough linear looking thing, but now I'm going to get a little bit more fine-tuned and get the correct concavity. So I'm going to draw something that is increasing and concave up. Let's see, we'll do this in blue here. So it's got to be increasing but concave up until we get to there. And then it's still increasing, just like that purple guy was still increasing, but now it's concave down, something like that. And now what changes at the top? It starts to decreasing, but still what? Still concave down. And now what changes? Still decreasing, but concave up. So the purple thing you would erase, but I like having it there. For me, it's just too much to handle all in one shot. Nick?
Maybe it's just coincidence. Sort of looks like
You're saying that F looks like it's shifted from F prime? Yeah. So it is a coincidence of these two graphs. It's a great observation that getting from the one to the other just looks like maybe we've shifted a little bit left to right. What does that first graph look like? Looks like a sine function. The second graph, like cosine, except it's upside down, right? Like cosine would normally start up here at 1. Yeah, but the fact that sine and cosine are very intimately related by derivative relationships is why. But normally the two graphs will look hardly anything alike. Yeah.
So that's
Yeah, I would say that. We didn't pay much attention to the y values here. Just a rough sketch. That's a good way to say it. Other questions on this?
do you know that it would be below the x-axis?
No, so I mentioned that like I picked this purple point up here at the top and I just made my graph hit that one, but any vertical shift of this one would be totally fine.
Yeah, the one I drew in my notes is just all like the lowest points are sitting on the x-axis.
Well, that's wrong. No, I'm just kidding. It could be anything at all, right? Just shift it as far up or down as you want. All we said was increasing, decreasing, concave up and down. And that says nothing about where the graph lives. So any vertical shift of this thing.
Is that like related to that plus C?
That's the plus C,
Right.
Which we have no way of knowing. Yeah, good. Okay, next page. So this thing will look familiar, just like last class. The Fundamental Theorem of Calculus Part 1 can let us actually calculate values of an antiderivative from the original graph if we're able to find the integral by looking at areas. Let's give this one a shot. We've got a function y equals f prime. I will label it y equals f prime of x. And it's pictured between -4 and 4 on the x. The function consists of two lines and a semicircle. And then it says f of -4 is 1. That's a particular point that we are now honing in on. So now there's only going to be one graph that actually hits that point right there. F of -4 is 1. Let's actually fill in this first part of the table. F of -4 is 1. Easy. Right, we're just filling in y values. And now let's go ahead and calculate f of 2. F of 2. Okay, so we're going to do the fundamental theorem. And it's going to start like this. So go ahead and copy that, and we'll talk about why that's the right place to start. We are after f of 2, which is why we put a 2 in this integral. We know f of -4, which is why that's the other number in the integral. It's the only two numbers we can put in there. And according to our fundamental theorem, well, remember, it looks like this. Integral from a to b of f prime of x. It's important that it's an f prime in there and that it's f's on the other side of the equation is f of b minus f of a, top minus bottom. So according to that theorem, what is this purple thing equal to? F or f prime? That's f of 2 and then minus f of -4. All right, that's the fundamental theorem. Okay, what can you say about f of 2? That is what we were after. So we're quite happy to have that in our equation here. F of 2 is getting copied, minus. How about f of -4? That's 1, it's given. That's why we put the -4 in this problem. So we'll put a 1 right there. So solving for f of 2, again, hinges on being able to calculate the left-hand side. This integral, if we somehow knew what that integral was equal to as a number, maybe it's 17, just plop it right there and it's easy to find f of 2. But that integral represents what geometrically? What does it represent? It's an area. And so that integral is telling us to calculate an area. And sometimes we calculate areas on the graphing calculator, but if it's nice shapes that we can actually do areas by hand, that's another idea. And so this is asking us for an area from -4 to 2. maybe with your pencil, just kind of shade in real quick the area in question, -4 to 2. And hopefully we see that it is comprised of shapes whose areas we can calculate. There's not many of those shapes. -4 to 2. Okay, so for me, I've got 3 shapes from -4 to 2. I've got 2 triangles, and then what part of a circle? Quarter of a circle. And again, triangles and circles, we know. We don't know much about areas, but we know those guys. So we just calculate. Area of blue, what is it? That's a 1, right? Half base times height. Red, that's a 3, right? 3, half of 1, that's a 3 up there. Okay, how about the whole circle? It's 4 pi, right? Radius is 2, so pi r squared. Pi times 2 squared is 4 pi. But we don't want the whole circle, we want a quarter of the circle, so pi. Okay, so we've got our areas, 1, 3, and pi. So what is the value of this integral over here on the left-hand side? 3 plus the pi minus the 1, right? Anything below is negative. So it's really 2 plus pi. 2 plus pi. Everybody see where that came from? Everything above is positive, below is negative. -1 and 3 is 2 plus the pi. Oh, the blue thing there. Okay, and so now it's just a simple matter of finding f of 2. F of 2 equals, all right, what do we get? We add 1, 3 plus pi. Is that okay? So it was 2 plus pi, and then I just took this -1 that was already here and added it. Now we're solving for f of 2. Yeah, so add 1, 3 plus pi. Okay, so we can fill that in our table. We just calculated f of 2, and we got 3 plus pi. That's it.
So basically, we can have so area of our interval is like the f prime of x dx. You're setting the f prime of 2 minus, or the f of 2 minus f of -4
Equal to the area.
equal to the area.
Exactly. Yeah, that's what that highlighted yellow fundamental theorem says. Okay, so so you could play the same game to fill in the rest of this table, right? As long as you can calculate areas, you can use that same fundamental theorem over and over again. I think one of these is enough, so I'm going to have you start the activities in a second. If you want practice, you can try to fill in the rest of the table. But the key here, what you want to take away from this, is that if you can calculate the area, then you can calculate the y values of f. If you can calculate the area under f prime, you can find the y values of f. And this kind of gets back to what Sephora had asked on that previous question. Right over here, she said, is this, how did you say it? Is it x accurate but not y accurate? Yeah, I think that's a really nice way to frame things. All we did was pay attention to the x values. And we said, oh, from here to here, it's increasing and concave up. And then from here to here, it's increasing and concave down. But we paid no attention to the y values. Well, we could pay attention to the y values. If I wanted to do some exact calculating, if we could figure out what that area was, and if we had, for example, a particular starting point, let's say that we were given that you got to hit that starting point there on the y-axis, how would you calculate the next y value? Like I just sort of randomly put it here, but if I wanted to be really precise, what would I do? We'd just figure out what the change is. It's the same, like it's the same problem that we just did. That fundamental theorem would just say, hey, if you know the area under the f prime, you can calculate the y value precisely. We need one y value, just like we had f of -4 was 1 in that case. Yeah. So, you know, it's kind of nice to recognize these are two sides of the same coin. The thing we did with increasing and decreasing in concavity was just very rough, but if you want precise y values, you need to be able to calculate areas. Okay. All right, good. Let's move on to the activity, which is right there. If you can calculate the area under f prime, you can find the y value of f. Great. All right, so let's see how far we can get in today's activity.